So what we're going to do today, as I said, these next couple of weeks are going to be, I'm going to widen your perspective. I'm going to take you beyond the track and to show you how the rest of the railroad world also works a little bit. And we're going to do it from the perspective again of derailments and accidents. But let's see. So today we're going to talk about wheels, axles, bearings, bogies, and other mechanical related problems. Next week's going to be what I consider to be one of my more fun type of classes, because we're going to talk about human factors and operations. We're going to talk about all the things people do wrong. And in spite of all the technology that we keep bringing to bear, which works, but does in fact, we still have problems that we deal with. And then the last class will deal with level crossings and switches and turnouts. So today, let me share my screen, and let's see, wheels, axles, and bearings. Okay. Okay, why? My computer seems to be a little bit slow. There we go this morning. Okay. Can everybody see my slides?
Yes, Alan, we see.
Yes.
Okay, very good. Okay, so we're going to talk about wheels, axles, and bearings today. So, by the way, when we talk about wheels in particular, you're going to see that in a sense, a lot of the problems of wheels are mirror images of the problems we see at the rail. And as we get into it, we'll talk about it. But the reason is really wheel steel and rail steel are very close to each other, and the contact stresses are obviously the same because the wheel and the rail are in contact with each other. So the wheel rail contact stresses are the same. So a lot of the wear and fatigue, particularly fatigue related problems, and even some of the crack propagation problems that we'll talk about for wheels, you'll recognize, you'll see they're mates of the rail. So let me start off with one of the great discussions that always goes on, even before I get to the derailment. One of the always issues that comes along when you talk about wheel materials and wheel hardness is which should be harder, the wheel or the rail? Because rail wear and wheel wear are both major replacement criteria. Wheel flange wear is the #1 replacement criteria for wheels in just about every system, and certainly metros see that a lot, where flange wear is what dominates the reason for replacing wheels. But also, even for railways, wheel flange wear is a major issue. And rail wear is a major replacement criteria as well, for particularly in the UIC world where the axle loads are a little bit lower. So the percentage of failures due to wheel versus rail sort of moves towards the wear side. So there's an ongoing controversy that sort of says, what should be harder, the wheel or the rail? Which is sort of saying, which should wear out first, the rail or the wheel? Obviously, the track people want the rail to be harder because they don't want to replace the rail as much. And the mechanical people want the wheel to be harder because they don't want to replace their wheels as much. In general, but not universally, But in general, wheels are a little softer than rails on purpose. And the reason is just generally easier and less expensive to take a vehicle into a shop and replace an axle set than it is to go out into the track and replace a curve of rail or a kilometer of rail or a given length of rail. I mean, the relative costs, the costs of the steel on a per ton basis are comparable, but the cost of the labor associated with replacement, as a rule, is is a little bit more higher for the track than it is for the wheel. So generally speaking, we tend to see the rail to be a little bit harder than the wheel. Not significant, not massively amount, but significantly amount. We'll talk about that a little bit more. But that becomes one of the real interesting design issues that you come in when, again, we see this more in metros and everywhere else, where again, very often you have one set of designers designing the vehicle and mechanical side, and you have another set of designers designing the track side. And as I've indicated before, they don't always talk to each other. They're supposed to talk to each other, but from personal experience, I will tell you that they don't always talk to each other so much. So very often issues related to the interface between the wheel and the rail for metros and light rail systems particularly can sometimes get lost in the cracks. And so this issue of wheel versus rail hardness often pops up as well. Okay, I digressed a little, but I wanted to introduce it. I wanted to sort of show you the relevancy of the of the system we're talking about. Okay, so you see this nice pileup over here. Okay, this is a pileup that occurred in Germany on the Deutsche Bahn in 1998 in one of their high-speed rail line, the ICE trains, Intercontinental Express. This is the German high-speed rail. This is historically has been the worst disaster in the German railway system, or certainly in the high speed. I think this is the only major high-speed rail accident that Germany had. Now, again, if you look at the picture, you can see why it's not so easy to jump to conclusions and say, oh, there's an obvious cause to this. Well, this one was even more difficult to find. And as I will show you in a few moments, all sorts of false leads were followed before they ended up finding the cause. Now, so sort of to give it away, of course, since the topic is wheels, axles, and bearings, the cause is going to be a wheel, axle, or bearing. But just the same, this was a very classical type of derailment. Okay, so this ICE train derailed at about 200 kilometers per hour, 125 miles an hour, and actually hit a bridge. You actually can't see the bridge anymore here because the bridge collapsed on top of the train. But it actually, when it derailed at 200 kilometers per hour, it hit one of the supporting members of the bridge, one of the vertical support posts, and actually literally brought the entire bridge down on top of the train. This was also, I think, one of the nastiest accidents in modern German history. 101 people were killed and another 88 were injured. So this was a really, really nasty accident. It actually happened on the major north-south line of the Deutsche Bahn, and you can see the site was a little bit north, not far from Hamburg, between Hanover and Hamburg, Germany. Okay, the train was the ICE 884. There was a power car on either end. And ultimately, it was found that the first vehicle off, the vehicle that actually derailed was this particular wagon, which was the fourth wagon in the consist. What actually happened was the front three wagons actually went. We're not actually involved in the accident. They went past. So you had the front, the lead locomotive and two wagons were sort of off over here. What you're seeing over here is the trailing locomotive. This is the locomotive at the end of the train. And you sort of look closely, you can see pieces of the bridge over here that collapsed. You can see this is multiple track territory. This was 4-track territory with the high-speed train running on, I think it was the number 2 track. There we go. So the high-speed train was actually running on this track northbound. So south of the bridge, which is sort of down here, there's a switch or turnout that leads to changing the tracks from the fast lane. The 2 inside tracks were the high-speed tracks. The 2 outside tracks were the slower speed tracks for the local. So as I said, the engine and 2 cars went past, and they stopped about 300 meters past the bridge because they obviously got disconnected from the train. So the first car, the number 4 wagon, plus everything behind it, smashed into this support post of the bridge, and there was enough energy, enough force involved that it actually broke the whole. Collapsed the whole bridge on top of the wreck. Initially, they thought they thought that this particular switch was at fault, was improperly set, was the cause for the derailment. So that was one of the initial thoughts involved. Again, you can see the pileup. Again, imagine trying to find the cause. The cause, as I said, was a broken wheel, but imagine just trying to find a broken wheel in this mess. It's not easy. Okay, so like most accident investigations, they came in bits and pieces. About 6 kilometers from the derailment site, some passengers reported a shudder, a shaking in the mid-train cars, so the wagons in the middle of the train. That was about 60 seconds before the train stopped. 2 kilometers before the derailment site, the engineer felt a tug, and the disc brakes were applied. And there was a loss of braking from the lead locomotive. The lead locomotive, which has engine braking or regenerative braking built into the traction motors, apparently that failed. Okay.
What is a tug, please?
Say again.
What is a tug?
A pull. A tug is a pull. So the engineer felt that there was something pulling. He felt a pull on the train, some sort of longitudinal force along the direction of the train. So the crash layout, the one power car, the engine and 2 coaches, as I said, cleared the bridge and traveled north for about 300 meters when they stopped. The 4th car was the one that hit the bridge structure. The 5th car was severed in half by the falling bridge. Cars 6 and 7 were severely damaged and parallel to the bridge. Cars 8 and 9 were crushed under the bridge deck. Cars 10 and 11 actually piled on top of them. So you can actually see some cars were actually on top of some wagons were on top of other wagons. And then the number 12 power car was the one in the back. here. Okay. So as I said, there were 4 false starts before they finally found the cause, which unfortunately it happens often in complex type of accidents. So at one point, somebody thought an automobile fell from the bridge and hit the train. That's not as unusual as it sounds. There have been reported derailments. There was a very famous accident in the UK, in England, a number of years ago, where a car fell off a high cliff off a sideway, fell on the track, caused one train to derail, and that train, when it derailed, fouled or the second track, the adjacent track, and then a train coming from the other direction hit that derailed train as well. So that one particular automobile derailed 2 trains, not just one. So that was the first theory, but there were no cars on the track, so that ended up going. So then there was a second theory that one switch over here was put in the wrong position, and that caused the accident, but it turned out not to be the case. Then there was some consideration whether the train was going too fast or it was overspeed. Oh, sorry. This one was that a construction crew left the switch unprotected. Here, with the pitch was improperly setting. But in both cases, there was concern about that particular switch. And then after all these were ruled out, it turned out to be a broken wheel. But this was actually a very, very complex failure. This wasn't a simple failure. Most railroad wheels are solid monoblock wheels, which means okay. Let me make. Okay, just muted everybody. Most railroad wheels are monoblock wheels, means that they're solid wheels. The wheels are one piece, either cast or wrought. We'll talk about that in a moment, how they're manufactured, but they're one solid wheel. And the original ICE trains were also fitted with monoblock wheels. But there was concern about excessive vibration coming through the suspension, because the suspension was a steel spring suspension. Didn't quite have the damping as some of the more sophisticated rubber suspensions had. And so they borrowed a technique that you see in a lot of metros. A lot of metros also, to reduce vibration, have adopted what they call a tire around the wheel. So basically, instead of having the wheel being in one piece, the wheel has 2 parts, an inside part and an outside part, which has the actual flange. The outside circumferential part is referred to as a tire. And then there's usually some sort of rubber strip or rubber element that's placed between the inside solid wheel and the tire to reduce vibration. As I said, this is a design you see a lot in metros, and it's worked very successfully in metros. And so in around 1998 or so, the Germans decided that they were going to adopt that solution. And introduce that technique to their operations. And they use what was called a Bochum 84 type of design. That's a specific design of the tire wheel elastomer configuration. But what ended up happening was that there was a crack. Oops, I was trying to change the color. What happened here? there was a crack that started to grow internally between in this internal wheel inside the tire. And unfortunately, it was impossible to detect. Ultrasonic testing of wheels is still in its infancy. And in 1998, it was not. Even today, ultrasonic testing of wheels is not a very common practice. It's done very, very sporadically, and only limited railway supplies to do that. And that's because the ultrasonic inspection technology for a wheel is not as sophisticated or as advanced as it is for the rail. And so and being inside the tire, it was impossible to visually identify the crack during during inspection. So this crack basically grew until it became critical, reached what's called a critical crack length, which we'll talk about in a few moments. And then the critical crack length was such that it just propagates very rapidly, and the wheel fractured in operation and caused a derailment. So needless to say, the ICE trains went away from the tires. And at the moment, I'm not familiar with any major train, railroad passenger operations that uses a tire configuration such as this one, even though for metros and light rail transits, this still is a very, very common configuration and is still commonly used. So obviously the tire was an issue. A couple of other issues that came up, and it's worth mentioning because we'll talk about it a little bit later as well. The ICE trains were made out of aluminum to keep their weight down, and as a result, they had relatively low structural strength. And the German report for the accident afterwards basically came out and said that the crashworthiness properties of these cars were poor. Now, what's crashworthiness? Crashworthiness is a concept that's absolutely critical nowadays in wagon design, particularly passenger wagons. It's basically the survivability of the vehicle, or particularly the people within the vehicle, in the event of a crash. Now, obviously, you don't want a derailment to occur. You don't want a crash to occur. So the number one prevention method is the number one method to address the problem is to prevent it. Is prevention. But as we spent an excessive amount of time last week talking about, we haven't prevented them. We still have the occasional crashes for a variety of reasons, and we'll talk about them this week and next week, etc. And so the second line of defense is to increase the strength, and not only the strength, but in some cases the energy absorption capability of the cars, of the wagons. So a lot of the modern wagon designs, for example, are built in a way like an accordion with a crumple zone, so that if in the event of an impact, they absorb energy as they crumple, as they compress, and that again is designed to prevent or to protect the lives of the people inside. Now, just to make this point further, right around the same time as this ICE crash, there was a very famous broken rail derailment in the UK. We talked about that actually in our previous class, and the previous sessions were back last summer. And that particular broken rail crash in the UK also occurred at about 200 kilometers per hour. So for all practical purposes, the amount of energy associated with the crash was similar. But in that particular crash, approximately 3 people were killed, which is still tragic, but a lot less than 101 people who were killed in here. And one of the reasons the British at that time, and their report said that there were so few, relatively few fatalities in such a major crash, was because those particular wagons had very good crashworthiness capabilities. In other words, they had very high strength, and they were designed to withstand large-scale loadings, and they protected their passengers a lot better. So this is an issue. Over the last 20 years, there have been several major upgrades to the standards of particularly passenger wagons dealing with crash worthiness, so that most modern wagon standards do have provisions for crash worthiness. But it's a concept that I want everybody to understand because it's a very important one. A second issue, which was sort of unique to the Germans at that time, was that the bridge was very close to the railroad track. It was considered to be a secondary bridge, not a primary bridge. In other words, it was not a major highway, it was a smaller highway. And there was a very, and the bridge pillars were very close to the outside track. And subsequently, standards were changed to make to move the bridges further away from the track to avoid this type of problem. There was also an issue of the type and frequency of switches or turnouts you put in high-speed rail track. But unfortunately, you must have some switches because you have to be able to move the trains from one track to another, or from one track to a station. So again, that becomes a more difficult type of situation to discuss. Okay. Now let's start talking about wheel derailments and wheels in general. So if we start looking, this is some US data that I took, but it's not all that dissimilar to what I've seen in the rest of the world. You can see a worn flange. Okay, so the flange that's my flange. So a worn flange is one of the major causes of wheel accidents, and we'll talk about how that does. It's basically a worn flange can actually slip in between a switch point and a stock rail, especially if there's a small gap between the switch point and the stock rail, and basically have the wheel go down the wrong side of the switch and cause a derailment. Damaged tread, buildup tread. This is the tread of the wheel right over here, which runs on the rail. It can be damaged or have plastic flow and build up. That's been a cause. Broken rim. This is the rim of the wheel. So that's a common cause. Broken plate. That's the plate of the wheel. That's a common cause. Those are sort of the bigger ones up there. And then you have sort of other ones. Interestingly enough, loose wheel, which is also associated often with differences in back-to-back dimensions of the wheel, is something that Washington Metro just grounded an entire fleet of Metro cars because of a problem associated with back-to-back wheel flanges and loose wheels. Okay, so here's a better picture of a wheel. So if we look up here, I'm going to put a rail upside down. So this is the tread of the wheel, and the tread of the wheel is what runs on the head of the rail. And this is what has our conicity, our 1 in 20 conicity, to allow us to give a difference in rolling radius between the inside rail and the outside rail. This is my flange. And my flange is what runs against the head of the side of the rail. So my flange, so my wheel is coming over here, right? This is my flange, goes against the side or gauge face of the rail. This is my tread, which goes against the head of the rail. Okay. This is my rim. This is my back face rim. So one of the key dimensions we use to determine whether the wheel matches the gauge of the rail, if there's no problem, is what's called the back-to-back wheel flange. So we measure from the back face rim from here on one wheel to the same dimension on the other wheel, and that gives us the back-to-back. Why don't we measure from the front of the wheel? Because this wears, and the back of the wheel generally doesn't wear unless you have a restraining rail. If you have a restraining rail like we talked about, then you will get some wear in the back-to-back. On the back of the wheel. Okay, this is the front face of my rim. That's the back face of my rim. This is my rim. This is my plate. This hole in here where the axle goes is the bore, and this is the hub. By the way, most railroad wheel plates are curved. There's a curvature. You can see it right over here, actually. And the reason for the curvature of the wheel is wheels can overheat when you have excessive braking. The most common example of overheating wheels due to heavy braking is when you're going down a hill, when you're going down a mountain, you're going down a long grade, and you're braking all the way down. That generates a lot of heat. As a method to avoid generating too much thermal stresses in the wheel plate or web is curved so that as the wheel heats up, it expands outward and straightens this plate out. And so it has a way of basically allows the wheel to sort of expand with the heat and not build up excessive stresses, thermal stresses, and that's one of the design features of virtually all modern wheels. Another design feature of most modern wheels is wheels are manufactured with a built-in residual compressive stress basically in the rim and in the top of the plate. Why? Because if there's a crack that wants to propagate, it tends to propagate primarily under tension. If I have a compressive residual stress, it's very similar to concrete tie design or concrete design in general, where you use a high built-in compressive residual stress to delay or to reduce the effect of tensile stresses. You can't eliminate the effect of very high tensile stresses, but you can diminish their effect by putting in a high compressive residual stress. And that we also do that in wheel design as well. Okay, now let me show you a different type of derailment, different broken wheel type of derailment on a freight train. This was a Canadian freight train. So it's built to AAR standards, so it's a pretty large one, 140 wagons, probably around 14,000 tons or so, 3 locomotives. February in Ontario, let me just tell you, was very cold. Just before 1 a.m. is very cold as well. Train was traveling at about 43 kilometers per hour. It was a messy one, so 20 cars left the track, including 5 cars that contain hazardous chemicals, including sulfuric acid and sodium hydroxide. So here you can see the broken wheel very clearly. This was an older design straight plate wheel. Remember, I just finished saying that most modern wheels have a curved plate. This was one of the older designs with a straight plate. And so it was not able to accommodate the thermal loading as effectively. and caused and generated a fracture. Now, one of the things that tends to happen, sometimes happen with a broken wheel, for example, is if the wheel has a piece brake broken off, as you see right over here, it can sometimes still continue down the track and still run, because this wheel flange will keep it on, and the rest of the wheel, there's a working flange of the rest of the wheel as well. And so what you'll very often see is if you have that type of scenario, you'll see an impact on the rail over here, 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 and this distance is basically equal to that circumferential distance, which is roughly pi d. Pi times diameter of the wheel. So it's not uncommon to see these kinds of, this is what we talked about yesterday, talking about the signature, the derailment signature. Is there anything that gives you a clue? This would be a very clear clue, especially if these were roughly pi d distance apart between strikes. This is what the other piece of that wheel looked like. Again, you can see where it broke off. Basically, this was a defect. It originated in the rim, so it originated just below the surface. Not that dissimilar to a detail fracture from shell. And we'll talk about that later, because that's actually, there's a very common wheel failure mechanism that develops that as well. Now, one of the other interesting things that comes out of this that's very worth noting is typically these wheels usually take a while to develop the complete fracture and separation. So you start seeing this as a partial crack and as a partial defect. And that usually shows up as a very high dynamic impact loads. So there is a technology, and we talked about that, I think, 6 months ago in the summer, but I'm going to spend a little bit of time talking about it later today. There's a technology called wayside wheel impact detectors, or WILDs. And the wheel impact detector measures the dynamic wheel rail force. And if the wheel rail forces are excessive, that's an indication that there's something wrong with either the wheel or the wagon. Again, we talked about it earlier in the context of surface defects of the wheel or surface defects of the rail, but it's more common, we usually a wheel impact load detector looks at these types of defects on the vehicle. So, as I said before, straight plate wheels are now pretty much forbidden in most railway applications. The curved plate wheel is much more common. But the wheel impact load detector, or WILD, do I have a picture of one? Oops. No, I'll show you a picture one in a couple of moments. But the wheel impact load detector is a technology that has become very, very, very common. Definitely in North America, where there are hundreds of these, if not approaching 1,000 of them in North America, where they're a wayside device. It means they're built into the track, and they measure the dynamic wheel rail impact force of every wheel going over them. And then if you set a threshold, it would flag it. For example, I mentioned in a previous class that there's an AAR, there's Association of American rule that says that any wheel impact over 400 kilonewtons, the wheel must be replaced. And the wheel must be replaced at the expense of the wagon owner, whoever that may be. So a lot of the wheel impact detectors are designed to flag at 400 kilonewtons or 90 kips. depending on which units you're using, to do this flag. You also have the ability of flagging them earlier. So this is an example of the actual history of the wheels involved in this particular accident. So the history of this particular wheel. So this particular derailment happened in January 2008. So you can see that in December of 2007. So this is in kips. This is a North American number. So remember that 1 kip is equal to about 4.5 kilonewtons, if you want to do a quick conversion. But basically, you can see that it was at 87 maximum value in December 29th, 2007. So this is a month before the accident. The day before the accident, it was actually at 106, which is past the 90 threshold. So it should have been picked up. By the time it got to the day of the accident, the 3rd of January, they picked up a load as high as 137 kips. So you can see, and by the way, the static nominal load is about 33 kips. So that's the static load. And this is the dynamic load. So you can see the wheel impact load detector actually picked it up for some reason, and this is something that that gets into the maintenance and management of information. The vehicle wasn't stopped and identified and checked, which it should have been when it hit 137 kips a loading, and so that was a bit of a failure. Usually most North American practices is at 90 kips, you sort of schedule the vehicle to be, the wheel to be replaced. And if you actually hit above 120 kips, which is about 550 kilonewtons, you actually stop the train and go out and take a look at what's going on and then proceed at a very low speed to the next place. By the way, you can also see that the L4 wheel. So this is the first axle left wheel. This is the 4th axle left wheel. Also had a very high impact load. And interestingly enough, here they changed out the L1 wheel, but they didn't change out the L4 wheel, which is that wheel, which after it fractured. So before we go further, let me real quickly show you a quickie video on the wild system, because it's something that I think is of interest. There is no sound on this video, so I'm not going to bother turning it on, but it just shows it. So the wild system actually is a series of strain gauges to measure the vertical forces that are located under these protective plates. So the vehicle comes along, each one of these protective plates is protecting a series of strain gauges which are measuring the vertical wheel well forces. So you can see, you can sort of see a good wheel, bad wheel, and then a bad wheel would be identified by signal. A bad wheel can be a spall, a shell, a slid flat, an out of round, all of which we'll talk about here, but creates excessively high dynamic impact loading. So again, we'll go back to this a little bit later. This is a slid flat. You can see a fractured flange. These There are actually the strain gauges. You can see the strain gauges now underneath again, this is protective coating, but you can see the strain gauges are under here. And in a later slide, I'll show you the exact configuration. The forces are measured by the strain gauges. They go to a signal bungalow where the results are then processed. And depending on the way the railroad decides to measure the rules, that information can be broadcast to the maintenance headquarters, can be broadcast to the locomotive engineer, can be broadcast to anyone who has a need to know what's going on. Okay. And again, this is an example of the kind of exceptions. Each wheel is measured, and you can see the in this particular case, there was a 55,000 pound wheel load threshold that was set by the railroads, and then alarm notifications can be set, etc. Okay. All right. So this is a typical railroad wheel. This is actually a UIC design. I think this is one of the UIC type designs. So again, this is my flange. This is my flange width. This is the top of my flange. This is my radius of the top of my flange. This is my tread with, this actually looks like it may have two different angles, which is not, which you actually, I see a lot of that in some of the more modern metros. Wheels will have two different flange angles. So usually 1 in 20 in the center, and sometimes even more severe going towards the outside, maybe even a 1 in 10. Then you have the flange fillet radius. This is part of the transition. It's from the from the flange to the tread, and all your key dimensions, which I won't go into a lot of detail. This is not, I'm not teaching you how to design a wheel. I want you to understand what the parts of the wheel are. Okay, so generally speaking, the height of the flange, which is this dimension, it's actually this dimension we see over here. This is my flange height, which is the distance between the tip of the flange and the nominal center of the wheel tread. That flange height will vary as a function of wheel diameters. For the larger wheels, wheel diameters, it can be 28 millimeters. For smaller wheels, it can go as high as 32 millimeters. And the reason for this is to make sure you have proper engagement, particularly in switches. The height of the wheel flange becomes absolutely critical when we're talking about engagement with switches. For example, at the frog guardrail, where you're trying to make sure that the wheel is not going down the wrong side of the opening of the frog, you need to make sure that you have good engagement of your wheel. Likewise, the wheel going through the frog itself, going from the wing rail to the frog tip, you want to make sure you have enough depth of wheel to engage the flangeway. There's also a relationship between axle loads and wheel diameter, with the heavier axle loads having larger wheel diameter. So you can see for basically a UIC freight wagon, which goes up to 22.5 metric ton axle loads, you're going to have a wheel diameter that's going to be between 920 and 920 millimeters and 1,000 millimeters, or a meter. As your axle loads go down, your wheel diameters go down. So as a result, metro vehicles, for example, have smaller wheel diameters than freight vehicles, as a general rule. Is everybody seeing my screen? A lot of quiet.
Yes, yes.
Yes.
Yes. Okay. I'm not going to go through this in detail again, because this is not a class in wheel maintenance. I just want to sort of give you an idea of the different types of UIC standards. And again, just like the track, the wheel maintenance standards are related to the speed of the wheel. So again, the speed of the vehicle. So again, I'm going to allow you to refer you to the appropriate standards if in fact you're interested. I suspect this is just more for the way of information. And again, again, I'm not going to go through this here. What are the types of different standards you have here? Just to show you a different type of wheel, this is an AAR, North American wheel profile. You can see the 1 in 20 taper on the tread of the wheel. This is solid all the way through. This is a fairly typical freight wheel for the North American market. This is the wheel flange. I should mention that wheel flanges come in various thicknesses, because as the wheel wears, you can actually cut the wheel. You can cut the wheel. So if I'm getting excessive wear, and I'll show you this in a later picture as well, I can come along and I can machine this wheel and put in a new wheel profile and reuse the wheel. This particular machining process is referred to as truing. And it's a very common international practice for allowing a wheel that reaches its wear limit to have another life, so to speak. So it can be taken into a shop, and there's a special lathe called the truing machine that will very often do all 4 wheels in a bogie at the same time and machine it down to a new profile.
I have a question.
Say again?
Professor, this is not done by lathing machine?
It is done by a lathe, basically. Yes, it's a special lathe that you see in the mechanical shop, because it's designed. It's a set of 4 lathes. You roll the vehicle. You roll the bogie onto the. You actually roll the vehicle onto the lathe. It takes all 4 wheels on the bogie and machines all 4 wheels at the same time.
Yeah. Thanks.
I also have a question.
Yeah.
Rima, we have an inclination in metro of the rail 1 to 40.
Right.
How it depends on wheel. Is this thread conicity of 1 to 20 because it's somehow connected to inclination of the rail? Do we have it different because we have different inclination or different wheel?
No. Okay. The short answer is it's not directly connected to the conicity of the wheel, because it serves 2 different purposes. The conicity of the wheel is designed to make up the difference between the inside rail and the outside rail as it goes around the curve. Remember, we discussed that earlier.
Yeah, that's right.
This is also called the cant, but the cant of the rail. And by the way, it's not just metros. Almost every railroad has some sort of cant, and 1 in 40 is far and away the most common cant in the world. So 1 in 40 is a very, very common cant. And the purpose of the cant of the rail is to basically change the wheel rail contact point and to move the wheel rail contact point a little bit more off center so as to reduce the wheel rail stresses. So the cant of the rail is more interested in defining where the wheel hits the rail, and the taper of the wheel is really designed to look at the length, the radius, the rolling radius of the wheel as it goes around the curve. So it has two different purposes.
I see. Thank you.
By the way, you can see here the flange angle of the wheel. I don't remember if we talked about the wheel climb issues in the previous class or not, but we'll bring it up again here too. But when we talk about wheel climb later on, you'll see that this flange angle, which in this particular case is 75 degrees for this design wheel, plays an important part in the potential of that wheel to climb up the side of the railhead. This flange angle is very important. And the flange angle changes with wear. And then you can see other key dimensions here as well. By the way, one of the differences you see in metro wheels, for example, is very often the width of the metro wheel is very different than the width of a railroad wheel. You know, for example, in some metro systems, you'll see a narrower wheel tread than a railroad. Likewise, it's an issue, particularly for light rail systems. The width of the wheel tread becomes a very, very important design issue when it comes to amount of overlap. Because if you're, for example, if you're a light rail in particular, the amount of overhang you have on your wheel is very important, because very often this is some sort of street material, be it brick or asphalt or concrete or whatever the material is. And as the wheel wears, this has a potential for contacting it. So sometimes you'll see in light rail systems, you'll see a narrow wheel tread, just to eliminate this type of overhang. So now let's talk a little bit about wheel defects. And like I said, I want to sort of try to point out the difference between this and what we're going to see in the rail side as well, because it's very similar. So among the wheel defects we see are thin flange. So remember the wheel. Okay, this, remember, was one of the most common causes of derailments. So typically, the thickness of the flange is defined. You can see here, this is roughly 1.156 inches. There's a thickness of this flange. Because this is running against the rail. Remember, the side of the rail is over here. So this flange is going around the rail. And when we're in a curve, we're flanging, we have flanging forces, we have wear. So this is going to wear down. There's a limit to which we allow that wheel to wear. But if you allow the wheel to wear excessively, this flange becomes very thin. And as I'll show you in a later picture later on, can result in a problem. We'll come back to that. I have some other pictures. I have pictures of all this as we come through, but I want to discuss it. But it will result in this flange can pick the space between the switch point and the stock rail. Can literally force, if it gets thin enough, it can force the switch point to open and cause a derailment. Vertical flange is when the tread wears. So let's go back here. This is a nicer picture to work with. So my height of the height of my flange, as you can see here, is defined to be 1 inch. So a vertical flange is when this becomes purely vertical, which is an undesirable situation because it can result in a wheel climb scenario. A high flange is when I get tread wear, and all of a sudden, this flange is no longer, if I have a lot of tread wear without a lot of flange wear, then this can go, say, from 1 inch to 1.25 inches to 1.5 inches. So it can go from 25 millimeters to 30 millimeters or 32 millimeters. What happens then is when I go through, if I have too high a flange, when I go through my frog, instead of riding on my treads on the wing rail going to the frog, I'm riding on my flange, because the flange, the height between the tip of the wheel and the tread is too high. And that sort of means instead of my rail sitting here or going through the frog, I'm actually riding on top here. And that again causes excessive stress, excessive wear, and can result in a derailment. That's a high flange. Hollow tread. And again, we'll show you this in more detail in a few moments. In a perfect situation, my wheel is over here, my rail is over here. So I'm going to get most of my wear here. So if my wear, and I'm exaggerating a little bit, but if my wear looks like this is a hollow tread. And you can see what happened. First of all, I lose my conicity, because my conicity is actually going in the wrong direction over here. And so all of a sudden my steering is affected, my whole ability to steer. An excessive high tread can result in very large lateral curving forces. Thin rim. Thin rim is when I get excessive wear, tread wear, and all of a sudden this rim becomes too thin, which means it's no longer, it has a potential of fracturing or failing. Out of round wheel, we've talked about in the past. An out of round wheel is when I no longer have a constant radius around my wheel, whether I have a flat or whether I have an eccentricity. In fact, what tends to happen, what tends to happen very commonly in railroad and especially a lot in metro wheels especially, is that we get non-uniform wear and we get what's called an out of round wheel. So and so an out of round wheel can have, if just exaggerating, if the out of around wheel looks like that, and there's sort of one piece that's out, that's an order 1. If I have 1, 2, 3 that are out, this is an order 3. If I have an order 12, there's been a lot of studies. In fact, I'm currently working with Washington Metro right now because they have a big problem with out of round wheels. In fact, most of the reason for taking wheels out of service for Washington Metro is that as the wheel wears, it wears non-uniformly, generates this out of round situation, which generates very high vibrations, which cause passenger discomfort and complaints. And so as a result, the wheel has to be taken out and taken to the truing facility, to that lathe, and has to be cut to get rid of the out of round wheel. So this is a very, very common problem, particularly in metros. Thermal cracking, where thermal cracks associated primarily with thermal forces due to braking. Shattered rim, where the rim fractures. Shattered tread, where the tread fractures. Tread buildup. If I have plastic flow, instead of having it down, it goes up, this sort of tread buildup can cause a derailment. It's another common wheel defect. So let's just show a few of these. This is a broken wheel, which we've already seen before. Loose wheel, where the wheel, basically, when you look at an axle, and we'll talk about this in one of the later presentations, when you look at an axle, there's a special seat on the axle where the wheel goes. If the wheel gets impacted and gets dislodged or moves off of that axle or becomes loose, then you run the risk of the wheel basically losing its side to back dimensions and no longer fitting into the gauge of the rail. Cracked or broken plate. Remember, this is the plate of the wheel. This is a fracture of the crack. This is the tread-worn wheel. So this is what I was talking about back here when I was talking about a hollow tread wheel. Also referred to as a false flange wheel. So this is very commonly called the hollow tread. So you can see how the tread has worn in, and it's typically called a false flange because you notice all of a sudden on the other side there's this high point. And if you recall back when we were talking about wheel rail contact stresses back months ago, I gave you a scenario where the low rail basically was contacted by this part of the wheel, this false flange, and this generates extremely high contact stresses and generates a certain class of surface defects and even corrugations associated with this. It also generates high stresses in here in the rail fillet as well. So this, if it's allowed to get very severe and again allowed to run to the top of the railhead, can generate some very high stresses in the rail and cause rail failure. Okay, this is sort of a extreme case where you can see the hollow tread, and you can see the worn wheel flange at the same time. And by the way, notice this little bit of plastic flow on the tip of the wheel. I just got a couple of months ago, Israel Railways just sent me a note about a derailment that happened where the wheel basically looked just like this. And we suspect this was the cause of the wheel climb derailment. But again, you can see the hollow tread. And you can see this very much interferes with the curving performance of the wheel. So this will generate very large lateral forces. Okay, remember rolling contact fatigue on the rail? Well, here's my wheel. Doesn't this look familiar? To include the angle that we see here due to slip. So this is the wheel half of rolling contact fatigue, which we can call surface, which in the wheel we call surface cracking or shelling. But it's basically the same rolling contact fatigue, the same type of stresses we see in the rail. And, you know, it can get as significant on the wheel as it gets on the rail. This is tread buildup. Remember, I said you have plastic flow where the material goes higher than the surface of the tread. Here you can see the tread buildup. These are actually different types of slid flats. So this is what a flat really looks like. So, you know, mathematically, you think of a flat as being just something that cuts across here, but in reality, it's much more complex than that. And again, there are gauges to measure slid flats as well as impact load gauges. Most railways have standards. So this would be a 50 millimeter, one large flat that's 50 milliliters long, or two adjacent flats that are about 37, 38 millimeters combined. A groove in the wheel. Flange damage. Very often you have a lot of damage in a derailment, and you have to make a decision what to replace and where to replace. Usually you want to replace almost anything that's damaged like that. Shattered rim. Remember, again, this is the rim. So there's a cracked rim, and a shattered rim is just a very much larger defect in the rim where this whole thing shatters off like that. Shell we talked about, thin rim from excessive braking. Every once in a while, you'll see asymmetrical wheel and wear on the two wheels in the same axle. Theoretically, the wear of both wheels on the same axle should be the same. Because, and for the most part, the number of left-hand curves and the number of right-hand curves go the same. For example, if you're a metro, you're going around the system, ultimately, the number of left-hand curves and right-hand curves tend to even out, and you tend not to develop an asymmetry in your wheel and your wear profile unless there's something wrong with your bogie. If your bogie is cocked, if your bogie doesn't straighten out all the time, but actually tends to orient itself in one direction over the other because of poor suspension characteristics, that's when you'll get this type of behavior. And in fact, this type of behavior usually suggests look at the bogie. There's a potential bogie problem. Okay, again, the thin high flange that we saw over here. This is what it looks like in real life. There's the plastic flow. As I said, I just saw something very similar to this in Israel Railways that was associated with a wheel climb derailment near a switch. So this is the black is the new wheel, the red is the worn wheel. You notice it's a little bit higher here because of plastic flow. Can't get to my bottom yet. So if I want to, if I take it to the lathe and true it, I can do this, and I can have a sort of another iteration of my wheel life. I can do that. Usually, depending on the design of the wheel, you can usually true it about 1 or 2 times, and then you have to scrap it. So again, you can see the thin flange. You can see the high flange. You can actually see the height from here to there. I'm not going to go through the gauges. We don't need to really worry about the gauges. This is the truing or reprofiling that I mentioned. You can see how it's cut, and you put a new wheel profile in there to match the original wheel profile. Okay, back-to-back dimensions are absolutely critical for maintaining the proper gauge of the wheel with respect to the rail. For standard gauge, UIC standards basically says the back-to-back is roughly going to be between 1363 and 1357 millimeters. Again, that's this dimension, or actually technically it's this dimension. And again, we measure here because this is where most wear curves. And again, the one exception for metros that have restraining rail, if you have restraining rail, then you will have wear on your back-to-back. And you have to be really, really careful that you don't have excessive wear, because that can cause, again, a situation where your wheel gauge does not match your track gauge, and you can have wheel climb or wheel drop in, depending on which direction you're going. This is sort of an ultimate loss of back-to-back spacing. You can see how this wheel has been pushed all the way down the axle off the rail seat. I think we can all agree that's not standard back-to-back. Cracked wheel. Again, you can see the fracture. This is actually a cracked rim again. Wheel tread failure. This is another type of wheel flat. Doesn't go all the way across, but wheel flats don't always go across, but you can see how severe this is. Again, this should look very familiar to the rail. I remember showing you pictures of this on the rail. You can sort of, if I would have chopped this off, you would have looked at that and said that looks like the rolling contact fatigue or surface falling that I saw with the rail. But again, the contact stresses on the wheel and the contact stresses of the rail are very similar. And as I mentioned, the steel is very similar. Again, surface falling. Again, if I didn't tell you this was a rail, a wheel, you can just as soon say it was a rail. Shattered rim. Fatigue. Gee, doesn't this look familiar? Up to and including the growth rings. Fatigue failure growing, in this particular case, from the tip of the wheel flange across, and then you can see from this fracture surface that this simply broke and fractured at this point in time. Now, in the wheel, not only do you have the stresses associated with the contact, but you also have stresses associated with heating and cooling of the wheel. Why? Because of braking. When you brake, especially when you're using tread braking, so the tread braking is applying tread braking here, but if you're going down a grade, if you're going down a severe grade, if you're going down a mountain, and you have your brakes applied all the way down, which is what you normally do, you can cause significant heating of that wheel. Then when that wheel cools off, then I have thermal crack and thermal stresses. So I have a tensile compressive cycle associated with the heating cooling of my wheel. This is the same wheel, but now you can see the whole wheel flange. And again, you can see the type of fracture that we're talking about here. Okay. wheel properties. UIC wheel steel runs to be about 235 to 300 BHN. So remember, UIC rail, if you remember, was running sort of in the 250 to 300 plus BHN scale. So just a shade higher than the wheel. In the US designation, and you have the same thing in the European designations, you have standard wheels. So you can see here my standard US wheel is 250 to 320 BHN, and you usually have a premium or a harder wheel, which is a 320 to a 363 BHN. In North American terminology, the standard wheel is called a Class A and the premium wheel is called a Class C. UIC designates it by a steel designation. So, you know, R7 is between 235 and 300 BHN. Here are some of the ER values, etc. And I mentioned there's a compressive residual stress introduced through a rim quenching. So you heat and quench the rim, and that introduces your residual stress. And that's designed to prevent crack propagation. Now, unfortunately, overheating of the wheel will basically remove and ultimately reverse the residual stresses. So the residual stresses, while in there when they're new, they can be changed, especially if the wheel is subject to very severe braking type temperatures. Okay, just to give you a quick feel for the different UIC wheel properties. Basically, again, if you look at it and you compare it to rail steel, not that off, a little bit more ductile. The ductility, rail tends to be more like the order of 10%. This is a little bit higher. These are the more common wheel steels down here, I guess. And these are older wheel steels, softer. You can see they're weak, they're softer, more ductile. Now we go a little bit stronger with a little bit less ductility. Okay, as I said, manufacturing of the wheels. Wheels can manufacture in one of two ways. They're either cast in place, and if they're cast, then the whole heating solidification process becomes really important. So this is a model of the solidification of a cast wheel. If they're wrought, which means they're fabricated out of a single block of steel, you have less of an issue with solidification. Okay, let's take a break here because I want to come back and I want to talk about crack failure pretty heavily here in the next few minutes. So let's take a break and we'll come back in a quarter to 15 minutes. So let's take a little bit of time now. Yes.
Gabriel Levy asked to remind you that he's on Miluim. He wrote you an email.
Oh, that's right. Okay. Yes. Thank you. I did. He did mention it. Okay. I just put a note down, so I'll remember that for next time. Okay. So now so we've been talking about crack propagation, and I've sort of been waving my hands and talking about crack propagation. And I think it's worthwhile learning a little bit about the mechanism of crack propagation. We actually had talked about fatigue before, and I think we briefly addressed crack propagation in the last go round. But I think it's worth your while to learn a little bit more about crack propagation, because crack propagation, while I'm going to introduce it within the context of wheels, it's just as applicable for rail. It's just as applicable for car body, truck bolsters. You're going to see all sorts of applications. Most steel elements deal with crack propagation. It doesn't have to be steel. It could be just about any material can have some form of crack propagation. So let's talk a little bit about the different types of mechanisms of crack propagation. So first of all, there are three primary modes of crack propagation. Most people are familiar with mode 1. Mode 1 is what most people think of as a crack propagation, where you have, if you look at this picture right over here, think of this as a little notch. Let's say we put a notch and a steel element in here. And if we basically lift up here and lift up here, so my loading or my stresses are designed to basically pull apart the two legs here, then the crack will propagate in the X direction, as you see here. So my loading is in the Y direction, my crack is propagating in the X direction. This is sort of classical. This is what everybody sort of thinks of when they think of crack propagation. So this is mode 1. Mode 2 is slightly different. Mode 2 is also my crack is propagating in the X direction, but my loading is in the X direction as well. So in fact, I'm actually having a shear loading here. So here, this is in mode 1, I have classical tensile loading. In mode 2, I have shear loading, but the shear loading is such that it's causing my crack to propagate again in the X direction. And mode 3 is where you basically have your crack is again propagating in the X direction, but your loading is in the Z direction. So here you're sort of almost, you can think of it as pulling it almost sideways. You're 90 degrees horizontal here. So again, mode 1 is, for all three cases, I'm looking for a crack to propagate in the X direction. In mode 1, my loading is in the Y orientation, vertical. In mode 2, my loading is in the X orientation, so it's a shear type of loading. And mode 3, my loading is in the Y direction, so it's actually it's also a shear type of loading as well. Plus there's a little bit of bending stress in here as well. So if we look at the crack growth rate, what we'll see is the crack length actually behaves in a very non-linear manner. We can have a slow rate of crack growth length and then a sudden propagation. And very often what tends to happen is when you reach a characteristic called the critical crack size or critical crack length, then that crack growth will actually turn almost vertical. And it's going to go like this. So basically at some point over here, you're reaching what's called a critical crack length. Now, probably, I think many of you have seen this type of problem in your automobile windshield. This is sort of the classical case. When you're driving down, particularly when you're driving on more rural roads, you have stones that come up and hit the windshield, and I'm sure many of you have had a little crack, a little indentation in your windshield. And it sort of nothing seems to, if you don't do anything about it, nothing seems to happen for a while. Maybe after a while it grows a little bit, very, very slowly, and very, very slowly. And then along comes a very, very cold day, and you have a very high tensile stress due to the cold. And all of a sudden you come out the next morning and your crack, which may be 3 millimeters, is suddenly 75 millimeters or 120 millimeters. You got this big crack in your windshield, and all of a sudden you got to end up replacing your windshield. I've had this happen to me a number of times. I'm sure many of you have. What you're basically seeing is the relationship between crack size and crack stress. And once you reach a critical crack load, crack size, the crack propagates very, very, very quickly. So it propagates very slowly initially, and then propagates very quickly later on in the mode. So one of the parameters that influences how the crack grows is what we call the stress intensity factor. The stress intensity factor, and you can see the units are sort of a little bit of a strange units, megapascals square root of meters. So the critical crack, the stress intensity factor, K sub I, is a function of the load itself, the load or the stress, the specimen thickness, the crack length, and then a dimensional and then a dimensionless crack length parameter. And once and basically my crack growth can now be defined in terms of that stress intensity factor range, or the change in stress intensity factor. Okay, so for 300 BHN steel, which is very typical of a wheel type of steel, my crack growth, dAdN, where A is my crack length and N is my number of load cycles. So my dAdN is the change in length as a function of load cycles, is equal to 3.1 times 10 to the minus 14th, which is a material constant, which we get from material testing, times the stress intensity factor range, delta stress intensity factor, to the 4.8 power. So what does this really mean for me? What does that do for me? Oh, by the way, how do I get it? I do lots and lots and lots of testing. Very similar to the SN type of curves that we got before, except these are crack growth rate terms, where typically we use samples that look pretty much like this. And so this becomes my load. And A is my crack length, or my additional crack length beyond the initial notch. And so you can see the confidence change is a function of the different types of steels that I have. And you can see this is a curve of dAdN against my change in stress intensity factor, delta K sub I, where K sub I is this term here. So this is an example actually for some rail steel, where again, the crack growth rate, dAdN, is a function of delta K sub I. And you can see lots of tests with lots of different types of material. In this particular case, there are 5 different types of steel. But you can see that they really define, they behave very cleanly within this range. Okay, so now let's go back to our equation here. dAdN equals 3.1 times 10 minus 14 delta K sub I to 4.8 for a wheel. And I come in and I tell you that my delta K sub I is 20 megapascals square root meter. So I give you my stress intensity factor range. So I have a value that's sort of over here. So dAdN is equal to 3.1 times 10 to the minus 14th times 20 to the 4.8 is equal to, so you calculate out, take it to 5.45 times 10 to minus 8 meters per cycle, because that's what dAdN is, right? Meters per cycle. So now we have something that can tell us something. Okay, so if my dAdN is equal to 5.45 times 10 to minus 8 meters per cycle, after 1,000 load cycles, my crack length is 5.45 times 10 to minus 8 times 10 cubed, which is 5.54 times 10 to the minus 5, which is 0.0 meters, which is 0.0545 millimeters. So after 1,000 crack cycles, my crack is basically 1/20th of a millimeter, 0.05 millimeters. So it's not very long, but this is a logarithmic equation, of course. After 10,000 cycles, my crack length is 0.5 millimeter. After 100,000 cycles, my crack length is 5 millimeters. I'm starting to approach failure. And after 1,000,000 cycles, my crack length is 55 millimeters, which is clearly a significant measurable crack, and that's over 2 inches. 55 millimeters is a significant amount. So again, we're back into the kinds of numbers we talked about on the rail side as well, when we were talking
Sorry,
about.
a question.
Yeah.
1 million. It's a frequency of the impacts.
Say again.
1 million loading
1 million
cycles.
cycles. 1
Is the
million load
impact-
cycles.
Is the
One-
impact
Yes, it can be. Let's say I have a wheel flat.
Mhm.
Okay. And so if my wheel circumference is 3 meters, then I would have an impact every 3 meters, right? So
Right.
basically 1 million cycles will be basically 3 million meters, right? So 3 million meters would be what, 3,000 kilometers? So in this particular scenario with this type of a load level, my crack would grow to 55 millimeters after 3,000 kilometers.
Okay, thank you.
Okay, but 20 millipascal square meter is a relatively low stress intensity factor. So what happens if I go up to 30? Now this is where my nonlinearity comes in. Remember, I'm to a 4.8 exponent here. So my crack growth rate now with 30 megapascal square meter is now 3.8 times 10 to the minus 7. So I've increased my load by 50%, right? But I've increased my rate of crack defect growth by more than a factor of 10. Because I've gone from 5.5 to 5.45 times 10 to minus 8 meters per cycle to 3.8 times 10 to minus 7 meters per cycle. So here, after 1,000 cycles, I'm already up to 0.3 millimeters. After 10,000 cycles, I'm at 3.8 millimeters. And after 100,000 cycles, I'm at 38 millimeters. Here, it took me about 1 million cycles to reach 55 millimeters. So to get 38 millimeters here probably took me what, about 700,000 cycles roughly. So 700,000 cycles to get the 38 millimeters here, whereas it took me 100,000 cycles to get here. So that's a factor of 7 roughly. If it was 40, if my stress intensity factor range was 40, then this would be reduced even more significantly. Everybody understand how this works? There's a problem. In Moodle, I've done what I've done before. Because I don't have time to do homeworks and grade homeworks in this class, what I've done is I've given you the problem and I've given you the answer. And it's in Moodle, and you'll see it. It's right next to the wheel presentation. It should be right underneath it. And I strongly encourage everybody to go through it, especially since you're going to have an exam. And you should know by experience that I like to give exams based on what I do problems in the class. So if you understand it and you do the problem, let me, you'll do well in the exam. If you don't, well, you have to work at it. So again, if you have any questions, if you have any problems with the problem, just email me. But it should be self-explanatory. I try to make it as self-explanatory as possible. So basically, as K sub I, as the stress factor increase, or the delta K sub I increases, the rate of crack growth increases, we see. And then K sub IC is that critical value in which the crack will propagate unstably. That's the windshield. That's your car windshield problem. The fact that it suddenly became cold, and the fact that it became. So remember, the K sub IC is a function of the load. So that there's your stresses in the windshield will be due to the cold weather, and the crack length is enters into the crack length as it gets better, as it grows. It's going to your K sub I increases, and the C sub 3 is also a function of the crack length. So again, your K sub IC, your critical crack intensity factor, is where it will grow unstably. In other words, basically, it's going to fracture all the way through. And we see this in rail, and we see this in wheel. So the broken wheels that you see are, can be a function of that. I see this in rail where remember where we showed, you saw it probably in the joint and the cracking from the bolt hole problems is a good example where you see this, where the crack suddenly starts growing slowly from the bolt hole and then propagates all the way through to the top of the railhead and the bottom of the railhead. So again, that's the same K sub IC critical crack size. And again, one of the things one of the parameters in our steel that we need to address this is a proper property called fracture toughness. And fracture toughness is a special test where you actually put a notch in there, not similar to a notch that looks like this. So a fracture toughness test is you take a piece of steel from the rail, from the wheel, from wherever you want to do, you put a notch in here, and you apply a defined load, and you measure how much that propagates, and that determines the fracture toughness of the steel. The greater the fracture toughness, the more resistant you are to crack growth, to rapid crack growth. Okay, so going on, switching to a different topic area, I want to talk a little bit about thermal energy from braking. Again, this is another problem associated with wheels. In this particular case, this is an actual problem that I dealt with the commuter railroads that had both tread braking and traction motor braking. So they had traction motors in the bogie on the axles, and they also had tread brakes. They had both. And they had a case where some of the axles, they had a problem with inoperative traction motor braking. The traction motor braking wasn't working. And so the tread braking was generating a lot of heat, and particularly because this was a commuter railroad where it was braking very frequently. So it was braking, it was basically a station every 1.5 kilometers. And so it would brake. The heat would not dissipate. The next brake would heat up, and there would be significant braking. And there was critical crack growth based on thermal loading. So the loading that we just talked about, instead of being mechanical loading, was thermal loading. And what we found was the number of braking cycles necessary to reach critical crack length was, of course, a function of the stress intensity range, exactly what we talked about before. So this is the number of cycles to reach a critical length. So instead of this being plotted as dAdn, what we do is we fix A. We say A is equal to, let's arbitrarily say 25 millimeters. And we take the number of cycles it takes to reach 25 millimeters. And as you can see, it's a function of the critical crack length. It's a function of the stress intensity range. By the way, these units are in English units rather than metric units. So they're PSI square, or a square foot, square inch actually. But the point that you can see over here is, in this particular case, when the traction motors were working and you were getting traction motor braking, the number of braking cycles to reach critical crack length was of the order of 1 million or so. Very, very high. When they had inoperative traction motors, it was of the order of a couple of thousand, which basically translated into a couple of days service. So they actually had the risk of reaching critical crack size in a couple of days. Why was this an important issue? Because the question was, how often should they inspect those wheels to make sure there's no critical crack inside the wheels? And the loading cycles in this particular case, there were 17 loading cycles per run, 4 runs per day. So they were really getting approximately 4 round trips a day. And based on that, they were basically looking at a 17 to 21 day inspection interval. Okay. Just to show you another broken rail derailment, I'm not going to go through the details of this. I just want to show you the wheel. First of all, here's the wheel. Pretty much shattered. So this is what I want to show you. This was a split rim. In fact, let's look at this one first. And so remember the wheel. This is the true wheel up here. You can see it. So there's the tread, there's the flange, and this whole portion here is the rim. So if you can see what happened here, you can see there was actually fatigue growth here. So what really happened, okay, so let's take a step back. The wheel fractured in 4 places, and it looked like there were a number of shells around all the circumference of the wheels, and the shelling damage, the actual fracture, this actual fracture initiated from the shell. So if you recall from our rail discussion of fatigue, we can have fatigue that's initiated at the surface. This is the case. If you remember, I talked about a failure of a Washington Metro rail where there was a corrosion stress concentration factor on the base of the rail. That was a high stress factor, and so that was a surface initiation because that was right in the surface. It can happen subsurface, which is really where most detail fracture from shells occur, usually around 6 millimeters below the surface of the material, point of maximum shear stress. Usually we see that in the rail, we see it in the wheel. And then there's a third class of fatigue, where fatigue is initiated at deep material defects. So this usually means there's some sort of macroscopic defect. There's some sort of inclusion in the steel. There's usually an impurity or an inclusion in the steel that serves as the defect source. So these are the most common types of contact fatigue failures that we see. Surface defects, usually with some sort of stress concentration point on the surface that allows that makes the stress maximum and initiates from there. Subsurface, usually around 6 millimeters below, which is the point of maximum shear stress, which is probably the single most common type of defects that you see in rail. And it's also a very common one in wheels. And then a deep surface and subsurface initiated defect, usually associated with some sort of material defects. In these two cases, you usually get the type of shelling we're talking about that we saw in this particular wheel. Up here. And in this case, it usually initiates deeper down into the material. Okay. So in this particular wheel, it was a vertical split rim, which is a fracture of the rim. And initiated approximately 6 millimeters down. How do we know this? Because we did a metal scanning electron microscope analysis of the broken wheel, and the 6 millimeter down is sort of the classical fatigue type of mechanism. In fact, it's very similar to what we see with the detail fracture for shelf rail. It's the same type. It's the wheel mirror of the rail detail fracture one. Subsurface crack was parallel to the tread. The shell was visible. There was also a secondary crack from the bottom of the shell down into the wheel. So the vertical split rim or the crack really initiated at the base of the shell. You can see this is about 6 millimeters down. And then propagated down. Actually propagated. And you can see in the wheel, down is in. The surface is the top. So this would be up and this would be down. So you can see the arrows are pointing to the direction of propagation. The arrows are pointing in the direction of propagation, down into the wheel. And so it fractured down. You can see it actually ended up breaking in 4 places, but that was because there was one initiation and then it would grow. And you can see, for example, this one actually propagated longitudinally circumferentially for a little bit before it turned radial. This one came straight down. So again, a lot of the causes of this, because we had all these shells, again, the wheel was shelled around the circumference and exhibited multiple surface shelling. So I don't have the picture of it here, but you actually see it right over there. You can start seeing some of the shell. You can see the shells right on the surface of the wheel right over there. So again, this is the type of thing that a wheel impact load detector should be able to detect. So again, most wheel impact load detectors are designed to trigger at between 400 and 600 kilonewtons. According to this data, Canadian National Railroads, which is actually a North American railroad. They operate operations in Canada and the United States. They have about 30,000 kilometers of track in rough numbers. So that makes them about the 5th largest railroad in North America. They have 39 wheel impact load detectors, and they remove between 25,000 and 30,000 wheels each year due just to impacts, just detected impacts. So they take this process very seriously. It turned out that there's a vertical split rim, what is a serious major category of failure. And again, less than 3 hours before derailment, the wheel that fractured recorded a reading of about 420 kilonewtons. So again, that should have triggered an action. But usually 420 kilonewtons is usually not an immediate stop the train and do something right now. But they registered this about approximately 430 kilometers from the derailment site. So that was that was a couple of hours, 3 hours before. So the wheel failed catastrophically. It was a big derailment. We skipped over it, but I just wanted to show you that type of cracking. So again, remember the P1, P2 force issues that we talked about. What we're looking at here, the Wild is measuring the P1 force, which is the force that we need to generate the highest maximum loads. So we talked a little bit about a wheel impact load detector. I showed you the video before. So underneath the plates that I showed you before were a series of strain gauges configured in this orientation. So in fact, and you can see they're on either side of the sleeper on purpose. So there are 4 strain gauges. One, can you all see this yellow, or should I switch colors?
See it.
You can see it? Okay. 1,
That's
2,
fine.
3. If anytime you want me to switch colors, let me know. 4. And there's another 4 on the other side. So you can see the 4 on one side, and 4 on the other. And then the wheel impact load detector has about 20 of these arrays, actually a little bit more, around 24 of these arrays scattered along. Because remember, you want to be able to catch the worst part of the wheel. So let's say my wheel flat's over here, and this part of the wheel just happens to go over this gauge, then I wouldn't detect this impact. So I need another gauge over here, and I need another gauge over here, and I need another gauge over here. So I make sure I pick up the maximum load. So that's why the wheel impact load detector was distributed over maybe 10 meters of track. And for those of you who are interested, that's how they're hooked up electrically to give you the shear. Basically, it's measuring, what it's doing is it's measuring the vertical shear here and the vertical shear here and subtracting the two, and that is the load itself. And there's that Wild detector again that we showed you from the video. Again, there is a strain gauge set here, 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 etc. And we discussed this previously with the previous derailment. Again, showing the wheel impact gives you it also gives you the speed. This is all in English units because I don't have access to any European Wild results, sorry. So there's the entry speed. There's the nominal load, which is the mean or static load. There's the peak load. And again, So this is approaching 400 kilonewtons here. And this is approaching close to 600 kilonewtons here. This is over 600 kilonewtons here. And you can see the ratio of peak to static is more than 4. And this is the left wheel, and this is the right wheel. So this is exact. Now you see the right wheel is also a problem here. Not as severe as that one, but I'm seeing loads of the order of 400 kilonewtons to maybe 450 kilonewtons. Okay. So that's inspection for impact loads. What about wear? How do we have, how do we inspect for wear? We spent a lot of time talking about wheel wear. Well, of course, there are mechanical gauges that you can measure in the shop, but just like we measure rail profile using lasers and video cameras, the exact same system can work for the wheel, except instead of it being on an inspection vehicle, it's now mounted into the track. So we mount our lasers and our video cameras into the track, and we can measure our wheel profiles, again, in a manner and using the very same technology. As a matter of fact, the people who make the rail profile measurement systems, like the people who make the rail measurement profile systems on on the Israeli railroad track recording car, also, it's a company called KLD Associates. They sell it to Placer, who puts it on the car. They also manufacture a wheel rail measurements, a wheel profile measurement system, which is becoming more and more popular. It's not as commonly used as the rail profile system, but we're seeing it being used more and more. And if you notice, the image here reminds you of the image you get from the rail profile measurement system. You can see you get a pretty clean measurement image. So you can look at flange thickness, flange height, tread width, and even rim thickness with respect to a reference point. So you can you can get several of your key wear measurements from this wheel profile measurement system. Now, I mentioned one of the big problems with a thin flange is it can pick a point. So if you look at your flange here, and this is a closed switch point. So this switch point is supposed to be closed. This is an actual switch point. I actually took this from some data that we took in the UK. So this is actually a British switch point where this is about, 4 millimeters wide, roughly. There's a gap, there's a 4 millimeter gap between the switch point and the stock rail in the closed position. And if this was worn with a little plastic flow at the end of it, it can actually slip into that gap and force that open. So one of the issues always ends up being, who's at fault? Is it the wheel or is it the track? And in typical railroad derailment investigation practices, the track people say it's the wheel, and the wheel people say it's the switch point. So again, this thin flange can be picked up by the wheel impact detector. We talked about overheating wheels and excessive high thermal forces in the wheels. We also have the technology. There's a lot of inspection and technology that's being developed now over the years. So we now have hot wheel detectors. So again, let me emphasize that most of the time, inspection technology for rolling stock is mounted on the track, and inspection technology for the track is mounted on the vehicle. Now, that's not universally true, because there are certain types of vehicle detectors that can be mounted on the vehicle as well, but they're very difficult they're very expensive because you need, let's say you're trying to measure overheated wheel. I can put some sort of thermometer or some sort of thermocouple on every wheel and measure the wheel temperature on the vehicle. But then I need to have a thermocouple on every wheel in my fleet. Every car has to have some sort of processing, software processing, and communication processing. Whereas if I mount it on the wayside, if I mount it on the track, and if I can measure every wheel, then I only have one local, I only need a limited number of sites because I can spread those sites far apart depending on how far I need to measure. And by the way, that's a critical issue, how far apart any wayside detection site is going to be. And then I can measure things like wheel temperature using this type of hot wheel temperature, which, and you can see over here, this is a hot wheel detect temperature. It's basically an infrared heat sensor that measures the temperature of the wheel. We'll come back to the bearings a little bit later, so we'll talk about this a little bit later. But this is the wheel temperature sensor, which we call a hot wheel detector. And very often what you tend to have is a wayside site which has multiple detection systems. So this has a hot wheel scanner. You can see over here it's looking at the wheel, has a dragging equipment detector. It has a hot bearing detector, and you can add other systems as well to this as you need it. You can add a wheel profile measurement system here as well, etc. This is a hot bearing detector system. But in all cases, if you have a wayside detection system, the instrumentation usually in some sort of signal bungalow with some sort of communications device to issue an alert either to the train driver or to the maintenance office or to both. Very often, the first level of alert goes to the train driver saying you have a problem with wheel number 14, stop the train. So if I had a hot wheel detector, and I found that the 43rd wheel in my consist is hot because I'm counting my wheels, is above a certain threshold, I would send a message to the train driver saying, stop the train, go back, go to your 43rd wheel on the left side, so left 43, and check to see if there's something going on with that wheel. Is the brake shoe sticking? Is there a problem? Is there a crack in the wheel? And just physically check it before you move any further. There is a start of developing of wheel crack detectors using ultrasonic detection. I have a video, which I'll see if we have time, I'll show it later. But basically, at its current stage, it's really designed for shop use. There is no system that I know of right now that can be used on mainline track to measure, look for cracks in wheels on mainline track. The systems that I'm familiar with require to go in low speed in a shop, usually using a water couplant, not dissimilar to your ultrasonic inspection of your rail, but looking for the wheel. And that technology is really now just starting to be used. It's still not that commonly used. Okay, so let's finish wheels and go on to bearings. So bearings, which are also referred to as journals. Most modern bearings are roller bearings, but the term journal bearing still applies, and it's still, so you'll still hear sometimes bearings referred to as journals. So again, the bearing is located at the end of the axle. I think I had a better picture actually of it over here, right here. So this is somewhat exaggerated, but you can see the bearing is located at the end of the axle. And then the bogie side frame goes over the bearing, over the adapter. Then the bolster goes across between the two side bearings, and then the wagon goes on top of the bolster. So basically I have a bearing for each wheel. I have 2 bearings per axle, 4 bearings per bogie, 8 bearings per for wagon. Okay. As I said, the bearing goes on the end of the axle. So this is my axle. This is where my wheel goes. This is my wheel seat. This is where my bearing goes. And then I have a collar to make sure the bearing doesn't slip off here. So this is an old-fashioned oil-based journal bearing, which you should almost never see anywhere again. Instead of your sealed bearings, this one has to be opened periodically and oil dumped inside to keep the bearings from burning up. They're really not commonly used anymore. They're in fact prohibited by most railroad operations. Okay, this is the journal, which is not the common bearing. The more common bearing is the roller bearing. This is the seal bearing that you usually have in all your equipment, be they freight wagons, passenger wagons, metro wagons, light rail systems. They all use some variation of the modern sealed bearing. Again, bearing goes on the end of the axle, adapter, side frame. Some variation of this design is used with every type of wagon. Okay, the bearing itself, a roller bearing is referred to with that because it has the bearings in here. You have an end cap at the end of the bearings. You have your seals. You have your cup of your bearing, which the cup, which is what retains the bearings. And then there is a sealed journal inside of here as well. And this is permanently sealed. It's self-lubricating. It's designed to go for a couple 100,000 kilometers before it has to be replaced. Has a finite life like everything else in the railroad industry, but it also fails. So failures include crack cap. The biggest failure, the most common failure, the biggest problem is when something happens internal to the bearing so that it doesn't frictionlessly or very low friction slide, but generates heat. And it can very, very quickly generate enough heat to burn off the entire end of the bearing. So the whole end of the bearing itself gets burned off. So here's an example of a derailment. Again, I'm not going to spend a lot of time talking about the derailment, but I want to show you what the axle looks like where the bearing burned off. And you can see that the heat generated by the burned off bearing was so high that there was plastic deformation of the axle. And the axle actually fractured at this point. And this is a very common mode of failure with the burned off bearings. And if you remember from the master statistics, and I'm sure everybody remembers all the statistics I threw at you last week, so feel free to go back and check if you want. But burnt off bearings, burnt bearings and fractured axles were one of the top UIC derailment categories. So this is a real UIC railroad issue. So in this particular case, there was a bearing measure inspection system, the old type, which is the thermal, which measures the heat. So basically, the problem with the thermal bearing inspection systems, the most common bearing inspection systems that I showed you a moment ago is basically using some sort of infrared system to measure the temperature. And if the temperature is above a certain threshold, you stop the train. You absolutely stop the train. This is a case where the bearing inspection system broadcasts a warning to the engineer and says, overheated bearing, stop train, go out and check. And in fact, most railroad engineers train drivers carry thermal crayons in the cab, so that if they have to go check an overheated bearing and overheating wheel, they can use a thermal crayon to see if it's a critical temperature and to make sure it cools down properly. The problem with the overheated bearing temperature is that a wheel can go from normal temperature to this type of failure in 50 to 100 kilometers. So depending on the type of failure you're dealing with. So if it's going to grow that quickly, that means theoretically I have to put a hot bearing detector every 50 to 100 kilometers, which is in fact what we see in many parts of the world where they're concerned about overheating bearings. So that if you have a 10,000 kilometer railroad and you're putting a detector every 100 kilometers, you have to put in 100 of these detector systems. If you're worried about failing in 30 or 40 kilometers, then you may have to start putting in 500 of these systems for a 10,000 kilometer system. So in this particular case of this derailment, the detectors were far enough apart that they didn't pick it up, or I should say the time it took to go from not measurable temperature to failure was short enough that it occurred between the detectors. There was no real indication of a failure at these detectors. And again, I mentioned what happens is the hot bearing detector, and again, you can see the hot bearing detector right over here. Remember, the bearings are outside, so this is designed to go up and measure the bearings. The signal is sent into the shed where there's the processing and the communication systems. And as I said, this communication system usually goes to the driver, right? As well as being recorded in the system. There was some concern here that earlier there had been some hot box detection. Oh, by the way, you'll sometimes have a hot bearing detector referred to as a hot box detector. Now, if you ever hear the term hot box, it means a hot bearing, overheated bearing. So again, there's my bearing. I want my infrared sensor to come up this way. So they're basically based on non-contact infrared measurement systems. Very simple, straightforward. Analog is no longer used. Everything's digital. Now, one of the issues, and this is really important for you to understand this concept, because this holds true not just to hot bearing detectors, for any type of inspection system. There are 4 possible results for an inspection system looking for a defect. So this is my inspection alarm, and this is whether I have a defect or not. So this is a defect, this is no defect, this is an alarm, there's no alarm. Okay, so what you want is you want your inspection system to properly identify a defect, which means to give an alarm when the defect is present. And you also want it to properly identify a no defect and not give an alarm. So again, let's use a hot bearing detector as an example, but it can be just as applicable for an ultrasonic rail defect tester or a hot wheel detector or an ultrasonic wheel detector or any other type of system I want. So ideally, I want a positive alarm if I have a defect, and I want no alarm if I don't have a defect. Okay. If I don't have a defect and my alarm turns off, that's a false positive. A false positive means my alarm says there's a defect when there's no defect. The other case, my false negative, is when I have a defect, but my alarm doesn't identify it. My system doesn't identify it. So, which is worse, a false negative or a false positive? Any thoughts?
False negative.
Well, a false negative is worse from a catastrophic point of view, right? Because if I have a defect and I'm relying on my inspection systems to identify it before it causes a derailment, and it misses the defect, then I have a derailment. Most broken rail derailments and most broken wheel derailments stem from false negatives. False positives, on the other hand, are very undesirable because they're an operations and maintenance headache. So let's go back to my hot bearing detector. Every time I have a false positive on my hot bearing detector, I have to stop the train. My train driver has to get out of the train. He has to walk back to that wheel on that axle, and he has to physically inspect it, usually with a temperature crayon if he's looking for heat-related problems. But if it's a wheel impact, if it's a wheel load impact detecting, if the wheel load impact detector said I had 620 kilonewtons, I want to go out there and see what's going on with my wheel. So false positives, while they will not result in a derailment, will result in a disruption of service. And in some cases where you're not sure what happens, you take it into the shop and you have to tear apart let's say I have a false positive in one of my bogey measurement systems, one of my L over V measurement systems. I may have to take the vehicle into the shop and tear apart the bogey, which is suddenly very expensive. So this can result in a derailment, which is sort of the worst of all cases, but this can result in very high costs. So ideally, we want to reduce both false positives and false negatives. And that is the key and the trick to properly developing an inspection system. So now let's go back to wheel ultrasonic testing. Wheel ultrasonic testing has really been around for 20 years. And I remember in the late 1990s, early 2000s, when wheel ultrasonic testings were introduced on a test basis on a number of railroads in the United States. And the problem was they generated a huge number of false positives. So much so that they were literally having to stop 20 to 25% of all trains for inspection, which is just totally unacceptable. So what ended up happening is they ended up changing the threshold and increasing the threshold greater and greater to the point where they were not able to properly identify defects. And that's one of the reasons why ultrasonic wheel inspection basically was put on hold for the better part of 15 to 20 years, and is only now reemerging as we develop better signal conditioning and more important signal conditioning, better analysis logic, better AI and machine learning and analysis logic to basically get rid of the false positives and identify the defects. So there's a lot of technology, particularly a lot of computer science technology going into reducing this and reducing this while maintaining these two at a very high level. Okay, So one of the other problems, as I mentioned, is that how far apart do you have to put an acoustic bearing detector? If you got to put it every 30 kilometers and I got a 40,000 kilometer railroad, then all of a sudden I'm looking at well over 1,000 bearing detectors. Even if I put relatively inexpensive hot bearing detectors, we're still talking about, a couple of $100,000 per detector. So if I have to put 1,000 detectors in at a couple of $100,000 per detector, I'm looking at a couple of $100 million. So all of a sudden, is there a better way? So one of the newer technologies that's coming out on the bearing side is what's called an acoustic bearing detector. So an acoustic bearing detector is designed, it doesn't want to wait until the defect gets large enough that it generates all this heat and causes the bearing to burn off. It wants to identify it much earlier. And it does it using basically an acoustical signature. So here's a series of acoustical microphones. These are nothing more than acoustic microphones that capture the sound of the bearings going by and then use filter signal conditioning to monitor the behavior to see if they identify the signature of certain types of defects. So like here's a large cone defect. So this is inside a bearing that's been broken out that failed, but didn't burn off because the acoustic bearing detector detected it. This is the signal frequency for it. This is raw, this is processed. You actually run it through a fast Fourier transform, and you can actually get the critical frequency bands. And so this is one of the defects for which there's an identifiable signature using the acoustic bearing detector. And here again, here's the fast Fourier transform. So this is the defect. This is the signature. You can see there's a 4 hertz peak. There's a 50 hertz peak. And I can't quite see the bottom, but this is probably somewhere in the 100 hertz peak range. So again, you can see there are some distinct peaks, and the 4 hertz and the 50 hertz seem to be associated with this particular bearing defect. So the presence of this peak says that I got a problem, flag that vehicle. So right now there are, and research is continuing as this, but there are certain types of defects like a broken roller element, a spun cone, a cone spall, a cup spall, water etching, all of which we've been able to identify critical frequency ranges so that we're starting to see more and more of these types of hot bearing detectors in service to supplement. We're not replacing the overheated bearing detectors yet. We're using them in complement, but as the ability of these systems grow to detect more of the full range of bearing defects that can result in overheated wheels, I would expect to see more of these and less of the overheated bearing ones, because these only have to be put apart maybe every 400 or 500 kilometers or every 1,000 kilometers, as opposed to putting them in place every 50 to 100 kilometers. Okay. Let me swing to axles, finish axles up pretty quickly, and then we'll take a break. So real quickly, here's another Canadian derailment, another messy derailment. Again, I'm not going to spend a lot of time on it. Now notice this bearing did not burn off. This bearing fatigued off. And in fact, this is the axle. So we're actually, the bearing, nothing happened to the bearing. You can see it was the axle that fractured. And in fact, you can see over here, again, boy, doesn't this look familiar? Here's my fatigue defect growth rings. And at some point, it grew to the point where the axle couldn't support the load, and it then just fractured. So in this particular case, the fracture ended up covering 65% of the axle cross section before it failed. And initiation point was basically stress concentration factors in the journal box associated with corrosion pitting. So there was some corrosion pitting being initiated in the journal box, because you can see the journal box was right next to the axle, but the corrosion pitting transferred off into the axle. Here's our typical crack growth length curve. This should look familiar for now. Again, this is a classical DADN. And in this particular case, this axle broke as a result of fatigue fracture that initiated in the axle journal fillet. In other words, where the bearing met the axle, that little fillet radius, there was corrosion pitting, distrosion pitting acting as a stress riser. And so the number of loading cycles the axle could make was decreased. By the way, axle size is geared to axle load. So a 33-ton axle load wagon will have a larger axle than a 22.5-ton axle load wagon, which will have a larger axle load than a 15-ton axle load passenger wagon, which will have a larger axle than a 12-ton axle load metro wagon. So question? Oh, so the corrosion pitting was due to the fact that there was moisture that occurred due to condensation when the bearings were cooling down. Normally, there's some sort of protective coating to protect it. In this case, it probably broke down. Okay. We finished. Any questions on wheel axles and bearings? Because when we come back, I'm going to sort of just talk about a bunch of other mechanical type of failures, just to give you a little range of feel for those. Okay, let's take a 15-minute break. Let's meet at roughly 10 after, and then we'll finish up.